Okay, this lecture is focused on measuring motor performance. So, first lecture we talked about motor abilities and motor skills, and within those we need to be able to measure how well we're doing at something. So, with motor abilities, we're going to look when we have our first kind of mini lab or our first lab. We're going to do a test out a bunch of motor abilities and look at how we might measure those. In motor skills, if I'm learning how to do something like tying a shoe or tying a surgical knot, or if I'm learning how to hit a baseball, swing a golf club, regardless of what kind of motor skill I'm doing, if we want to be able to measure someone's progress and how well they're doing in improving that and learning the skill, we need to consider how would we do that. So there are several common measurements that we can use in measuring motor performance. We're going to take a look at a number of those today. So a key question we look at then is what should we be measuring? So there's always tons of things that we can measure about a motor performance, but we need to do it with a purpose. So we're going to look at two main categories of measurements. The first one being performance outcome measures. A performance outcome measure measures something about the result of the movement or some kind of end product of the movement. So I think about some examples of that. If I'm looking at a sports skill like shooting a basketball, the outcome would be whether or not I made it or maybe how close I was to making it. For any kind of targeting task, it can be where did my object land? So a golf ball, how close was I to the hole? Did it land in the hole? So we're looking at some type of an outcome. Outcomes can be timing related, so we can measure things like sprinting time. That would be another outcome. So there are times where it's very important for us to measure outcomes. That gives us critical information about what someone's doing. The other things that we can measure sometimes are performance production measures. So these are the things that are happening or the movement characteristics that lead us to the outcome. So when we're looking at performance production measures, we can do this in a number of ways. We can do this in really formal quantitative ways where we're looking at maybe joint angles, taking measurements there, looking at things like velocity and acceleration. Or we can do things more qualitatively where we're looking at maybe some technique or formulated things. So if I'm trying to teach somebody a motor skill like hitting a tennis ball. So if we're learning how to do a serve in tennis, I need to figure out what do I think are the key components that go into a good tennis serve. So we're not just looking at where did it go and how fast did the ball travel. We're looking at the movements that created it and identifying some critical features in those movements that we think are important. So it's important to look at both the outcome and production measures. And we need to, in different skills, especially in complex skills, sometimes the production measures become important to know along with the outcome measures. So we're going to look just at several common examples of measures that we would see in motor learning literature that could also be translated into practice in all kinds of different venues, whether it be a physical therapy, occupational therapy, teaching, coaching, anytime where we're observing and monitoring a motor performance of some sort. So reaction time is a very common measure in a lot of motor learning literature. If we think about what reaction time is, I'm looking at the time from when I recognize some type of a stimulus until I make a response. So breaking it down a little bit here, we have three different components on here that are very closely related. So reaction time truly is the time from when a go signal is set off. So if I think about reaction time in sprinting, like in a track and field race, this would be the go signal is when the gun goes off. And then my reaction time there is from the time of the go signal until when I initiate my response. So my first start of a movement is the initiation of a response. If I think about a real simple reaction time task, sometimes we'll actually try this in one of our labs where we're going to do a really simple reaction time task where you're going to watch a computer screen, the screen will change colors, and then you're going to push a button. So the reaction time component would be from the time where the screen changes colors until when you start to move. Movement time is the time of your actual movement. When we combine those two, it's response time. So when I look at my actual, that real basic task that I just described where the screen changes colors, I push a button, reaction time would be the time from the go until the start of my movement. Movement time would be the time it actually takes me to push the button once I've initiated movement. So those two are very closely coupled, and response time really becomes what we actually tend to measure in that case. If I'm looking at sprinting in a 100-meter race, reaction time would be the time from when the gun goes off until when I first move, and then movement time would be my time that it takes me to cover the 100 meters. Okay, so with reaction time, there are several types of reaction time that we can study. I've just described with that computer task simple reaction time where there's one stimulus and one action. So I'm waiting for something to happen. As soon as that thing happens, I know my job is to push the button. Choice reaction time becomes more complex because we now have multiple stimuli and multiple actions. So I might have a reaction time task where when the computer screen turns green, I need to push the button, but it might also cycle through 4 or 5 other colors, and I need to know that I only push the button um, when the green one goes on. Um, I'm going to pause. What I've described is actually a discrimination reaction time task. So coming back down to that bottom one. So imagine a situation where there are multiple stimuli. So the computer screen could turn to red, it could turn to green, it could turn to blue, but I'm only supposed to push the button when it turns to green. So this is a go or no go task where I need to recognize should I be moving or not. A choice reaction time is similar, but what we would have there is we might have the screen could turn into 5 different colors, and each color corresponds to a different button. So I need to make a decision as far as which button to push. So I'm watching, I'm seeing what color comes up. If I see a red light come up, that means I need to push maybe the R key on the keyboard. If I see a green light come up, that means I need to push the G key on the keyboard. So it becomes more complex because I need to recognize something. I need to make a decision about which of several motor actions to complete, and then I need to complete that action. So we tend to see the time change. Looking at reaction time, we can break down. So we looked at reaction time and movement time and how those combine into response time. We can actually break reaction time itself down into 2 components, though. And what we're looking at there is a premotor component and a motor component. So a premotor component would be from the time the stimulus, from the time the go signal went, so if it was changing colors or if it's me responding to a sound, until I have my first muscle activity. So we can measure muscle activity with EMG. That tells us the electrical activity going on in the muscle. And so you can see here in the premotor component, there was the stimulus. My EMG is steady. Nothing has happened yet. And now suddenly right here, I start seeing some EMG activity. That's where our motor component starts. So the motor component, when we're actually engaging motor units in our muscle fibers and creating a response. And so EMG would be the way we would measure that. So and within reaction time, we have the premotor component and the motor component. And if we think about can we make our reaction time faster, it's very difficult to make our reaction time faster. And really, the component that we might have some control over is the motor component. So the premotor component, the time it takes for go through the process of recognizing a stimuli and then encoding an action to go out and actually happen, that's going to be largely very difficult to change. Okay, beyond reaction time, some other things that we tend to measure a lot of times in motor behavior research is error. So what we mean by error is not did you get a question wrong or something. What we mean is how close were you to what you were supposed to do. So if I'm doing something like a timing task where I'm supposed to start a stopwatch and then stop it at an exact time. So I want to stop that stopwatch at the actual time. I want to know how close was I to the actual time. So if we go to maybe a small middle school or high school track meet, rather than using an electronic timing system, we're probably hand timing. So we've got people standing at the finish line with stopwatches and they need to time when someone crossed the finish line. So what we'd be looking at is there's always going to be some error between when that person actually crossed the finish line and when they push the button on the stopwatch. So there's in a timing task like this, that's what we look at is one-dimensional error. There's only one dimension because I'm supposed to start and stop. There's one thing that I need to do. So there's 3 measurements that are common in the literature that we would use for those. There's absolute, constant, and variable error. What absolute error tells me is it tells me how far was I from the correct response in either direction. So it takes the absolute value of the constant error. So let's start with constant error. So constant error tells me how far away I was from the target, positive or negative. So let's imagine I'm hand timing someone in a race, and an electronic timing system would say that they crossed the finish line in 12.50 seconds, and my stopwatch says 12.67. I am 0.17 too slow, so that would be positive 0.17. If I flip that the other way around and I said I hit 12.33, I'm still 0.17 away, but now I'm in the negative direction. So my constant error there would be negative 0.17. In the first example, my constant error was positive 0.17. What absolute error does is it just takes the absolute value of that and it just tells you how far off you were. So there are times when absolute error is very good, and there are times when constant error is very good. In something like timing a race, I need to know, when I'm timing, am I consistently timing too fast or too slow, or is it evenly distributed? So in that case, I would probably want to measure constant error so I can see the patterns of if I was too fast or too slow. There are other times where absolute error is more important because we're just trying to know how close are we getting, whether it's too fast or too slow. Variable error, what that tells us is the standard deviation of our constant error scores. So over several trials, how much variability in there is there in our amount of error. So it's giving us an idea of how consistent we are in our timing errors. So if we're very consistent, we would have a small variable error. If we're very inconsistent, we would have a large variable error. So each of these three things tells us something slightly different, and they can all be fairly useful. So what we see in a lot of motor learning papers, motor control papers as well, we see that people will report sometimes all three of these and then allow the readers to make interpretations or for them to draw different conclusions from the different values. In other settings, we can have two-dimensional error. So two-dimensional error, what we'd be looking at is error in the x and y direction. So I want you for now to ignore the numbers and the rings that are on this target. Let's just imagine that this is a target that I'm supposed to throw a dart at. So I'm going to throw a dart. My goal maybe is to hit the center of the bullseye. Let's say I land up here somewhere where my cursor is. There's an x and y component to my error. So instead of just using these ring scores, we'll talk about that in a moment with radial error, what I would do is I would measure how far off am I from left to right and how far off am I from top to bottom. And that's going to give me an X error score and a Y error score. So two-dimensional error is very important in this type of a task because it gives us so much more valuable information about where are our errors, what do we need to do to correct them. Radial error is also a common measurement, but certain researchers would suggest this is maybe a weaker measurement. Radial error, basically, we're just saying, regardless of where I hit the target, we're going to measure how far in a radius am I from there. So you can see with these ring scores that this is radial error. So if I threw right down here, or if I threw up here, or if I threw right here, those would all give me a 7. So regardless of where I am, radial error would give us that example. Okay, a last type of error measurement we can look at is something that we would use for a continuous task. So remember back to the types of task, a continuous task is something where we're repetitively doing the same thing. So one example, we gave like things like cycling, we gave things like walking, running. Another example of a continuous task is balancing. So we're going to look at an example here of a balancing task. What we use to measure error in a continuous task is something called a common measurement. There are more than one, but a common measurement we would use is root mean square error. What root mean square error does is it tells us we can take a measurement every, say, 0.05 seconds, and we can say how far off are we right now. And so we end up over the course of maybe a 60-second trial, we have probably close to 60 times 20. We would have 1,200 time points we can look at there. So root mean square error basically uses a somewhat complex formula to say over the course of all those 1,200 time points that we just looked at, how far off were you? So it's kind of in some sense, an average of your error throughout that entire trial. So we'll do one lab where we'll use this task that I have in the video here. Try to get this set up. All right, internet works. Wonderful. This is called a stability platform or sometimes a stabilometer. And what the goal is here is to keep that thing level, essentially. So the person is just standing on there trying to keep that platform level. And every 0.04 seconds, what the machine is going to do is it's going to tell us how far away are you from level. And so then we would essentially take the average of all those to find out what root mean square error, find out how far off were you on average throughout the trial. Okay, so those were all performance outcome measures. We're going to talk now about some different performance production measures. So these are the things that are going on that lead to the outcomes. So we're going to look first at kinematic and kinetic measures, starting with kinematics. If you've had biomechanics or if you've had some kind of physics biomechanics, you would you would know a little bit about what these terms mean. So kinematics, I'm describing motion without regard to either force or mass. So I'm using variables like displacement, so how far did I move or how far did an object move? What was the velocity or the accelerations involved in that movement? So there are several measures we can take with that. We can look at movement as a whole. We can look at body segment movement. So I could look at the acceleration of different body segments. So I could look at the acceleration of the hand, the forearm, the upper arm in a baseball throw. And so all these things are going to give me information about what's going on to produce the movement. Kinetics, what we're doing is we're taking into account the consideration of force. So a couple of simple ways we might do this. One is measuring ground reaction forces. So the way we would do this is using some type of a force plate where we're standing on a force plate, and maybe we're going to do a vertical jump, and we're going to measure the ground reaction force created during the vertical jump. So that gives us a kinetic response because we're measuring the force clearly. And then another one we can look at is angular torque. So angular torque is the force in an angular motion. That's why we call it torque. And so I could look at the angular torque of about the elbow joint during a overhand throw. And so what that's going to tell me is that's going to tell me the force created as at that elbow joint as that person is going through the motion of a baseball throw. So again, these are just a different type of measure we can look at that will give us a little bit more information. Apologize for that noise. I'm sitting in a hotel room, the kitchen sink, and the kitchen sink is kind of a big gurgle. So if you're wondering what this was, okay. Another production measure that we can look at is electromyography or EMG. What we're doing essentially here is measuring the electrical activity in different muscles. So we can use surface EMG where we have just these nice little sticker electrodes stuck on. Other places we can use integrated EMG where they're actually kind of threading a needle through the muscle. We tend not to do that stuff because it's so much more invasive, and we can gather some pretty good information from surface EMG. What we're essentially looking at here is that we've maybe identified critical muscles that we want to evaluate, and then we're just measuring the amount of electrical activity at those. Common measurement we look at sometimes is percentage of maximum voluntary contraction. So I could give someone a couple different types of interventions and try to figure out which one leads to a higher percentage of their maximum voluntary contraction. So a maximum voluntary contraction is just when I'm contracting my muscle as hard as I can. So as much force as I can possibly produce with that muscle. And then I would see under some different conditions, how close am I getting to that max. So there's a lot of different things we can do with EMG. It becomes kind of an additional measure to help us learn a little bit more at neuromuscular level what's going on producing the movement. Okay, a couple similar measures we can look at are EEG and fMRI. EEG is similar to EMG. It's electroencephalography, I think. I might have missed a syllable in there, something like that. But we're essentially looking at the electrical activity in different areas of the brain. fMRI is different in that it uses brain imaging. So we see some images here. We're looking essentially at imaging that gives us an idea of blood flow to different areas of the brain while we're doing different things. So we're not going to go into depth in any of the EMG, EEG, or fMRI, but we just want to recognize that these are additional production measures that can help us to understand more what's creating the certain outcome that we're observing. Okay, so the most important thing again is we need to figure out what do we need to measure. If we're doing a research project, we don't want to measure something just because we have all this equipment, so let's just see what happens. We want a theoretical reason of deciding what we want to measure. In a practical standpoint, if we're looking at working in the field, there are times where it's going to be really important to know measures like EMG. There are times where it really does not matter. What we can look at with EMG, thinking about a practical solution, that's probably nothing that any of you all would work with. EMG is sometimes used in clinics as neuromuscular training in recovering from a lot of injuries or dealing with issues like that. One that has become increasingly common is actually using EMG as a measure to teach someone someone who has incontinence, to teach someone better control of their bladder. Essentially what they're doing is they're um, hooking up EMG sensors on muscles that would help to control the bladder, and teaching a person how to contract those muscles more effectively. And so that's a outside of the physical education, coaching, exercise science type realm. But that's a practical application. We can think about how that might work into physical rehabilitation, though. We could use something like EMG um, as a tool to measure muscle activity post injury when someone's recovering from a skeletal muscle injury. And so there are a number of things we could do there. A lot of times, what we might be most interested in is the outcome measures, but especially if I'm trying to teach someone different skills, I need some type of a production measure. I don't necessarily need to know the angular torque at the elbow joint when they're pitching a baseball, but I might, on a qualitative standpoint, need to recognize these are some critical errors or some critical features that need to be addressed in the form of your pitch. So again, we want to figure out what is the most important information, what do we want to get out of that, and do we have an effective way to measure it?